Yes, it's really true. There's only about a third of the semester to go. And, given where you started, you have come a very long way and you'll go even further. I hope by the end of this semester, you'll be very pleased with all the different things that you've learned in Data 8, not to mention all your other classes. Announcements today. Midterm regrade requests are due. You guys are doing great. Most of you don't have to change, well, almost all of you don't have to change anything. If you feel that a little bit of additional support will be helpful, there are tutoring signups that have been released. Today, we'll release a short project and a short homework. Now I'm solo today for a little while. Professor Wagner and Will join later. So if you could hold the logistical questions until Will is here, that'll be great. But if there's something easy that I can answer about what's on the screen, please let me know. I'll just pause for 1 second. It seems pretty routine. Okay, so where are we? Well, this week you learned percentiles and the bootstrap method, and Wednesday, we spent all of Wednesday talking about confidence intervals. And when you hear confidence intervals in your mind, you should translate that into English immediately by saying estimates, right? So these are estimates of an unknown number, and it's an interval of estimates because you are estimating based on incomplete information. So it's unreasonable to just say, oh, well, I know the number and it's going to be X. You say, I think the number is going to be in such and such range, and that needs both a computation as well as interpretation. And that's what Monday and Wednesday were about. And in that process, we noticed a few things. We kept using words like, we need to see what the variability is like in the estimates. Well, yeah, sure. And we can see those in our histogram, but there must be some way of actually quantifying them. A question, why do we use 95% as opposed to another percentage? 95% is common. It was our example, but there were also examples in which you use 90%, 80%. You can use any confidence level that you want. As we were doing those calculations, we were using terms like variability, which we should quantify. We noticed that some distributions come out bell-shaped. And in fact, the bootstrap percentile method that we taught for constructing confidence intervals only works if your empirical distribution comes out looking like that. So there's a real question as to which ones are bell-shaped, which ones are not. Why? Can we talk about that at all? Why is 95% the common percentage? Okay, I think it comes from the fact that 5% has become a common cutoff level for hypothesis tests. As you saw last time, some 95% confidence intervals can be used to perform tests. And because 5% is a standard cutoff there, the complement of that is the confidence level for the interval. One other question we're going to answer besides variability and the shape of the distribution is something that is a very natural, and that we've been saying that the sample size affects your accuracy. And there's a natural sense in which bigger samples should be more accurate. Right? We just feel that you have more data, it should be more accurate. So how do you actually talk about that precisely? That is all going to depend on being able to quantify center and spread of distributions. And so the idea today is to go through very swiftly some measures that you already know, and then talk a little bit more in detail about measures that will be new, or even if they are not new, maybe will just have been discussed as here's a measure. But always in Data 8, the point is, why is this the measure? Why not 3 other measures that I could come up with? And I hope to be able to give you very strong data science reasons for why we use certain measures much more than others. Right. So the questions are, how do we quantify the natural concepts we've been using, center, variability? Why do distributions come out, some distributions come out bell-shaped and others not? And how is sample size related to accuracy? So what we'll do is we'll start with center. Now, the median is one measure of center, but you know that the average is another. In fact, we've been using the average quite a lot. When we did some hypothesis tests, we said, oh, under the null hypothesis, the average of these two groups should behave in such and such way. So it's a great idea to note, just have in one place some properties of averages that we should keep in mind. Another name for the average is the mean. So everything that we're going to say can be illustrated by simple lists. I've taken a very simple one, 2, 3, 3, 9. It's average, the standard calculation, add up the numbers and divide by however many there are. Notice a few things. The average need not be a value in the collection. You know that the way we define percentiles, every percentile is a value in the collection, but that is not true of the average. It need not be a whole number, even if all the data are whole numbers. And you must not round. The average is 4.25. What it means, we'll discuss in just shortly. But the point is that the average does not need to have the integer type, even if the list does. Okay, it's somewhere in the middle. It's always going to be between the minimum of the list, but the maximum of the list, but it does not have to be halfway in between, as we will see, and you probably already have guessed. It has the same units of the data. This is important. If these were $2, $3, $3.99, then the average is $4.25. Okay, and it is going to be important later to think of the average as a smoothing operator. So continue to think of these as the amounts of money 4 people have. All right, so one person has $2, 2 people have $3 each, and one person is very rich and they have $9. So they have different fortunes. What the average does is it says, everybody put all your fortune into this pot. So everybody sticks the whole lot in, and then the average divides that evenly among the 4 people. So it smooths out the variability, the inequality, if you like, in the fortune. So it is a smoothing operator. And let me quickly go through some calculations that helped, for which some visualization is helpful. Questions about what's on this slide? Right. So here I have the same list, 2, 3, 3, 9. The average is gotten by adding up, sum the values and divide by however many there are. So sum of the array divided by the length of the array gives you your average. There's a NumPy method, np.average. There is also a NumPy method, np.mean. Okay, and so now what I want to do is I want to look at the calculation in more detail. So you know that the list is 2, 3, 3, 9. So we're going to do 2 plus 3 plus 3 plus 9 divided by 4. The point is not the answer. The point is what's going on in the calculation. All right, the answer we know is 4.25. Okay, so if you look at this, the calculation says first do the addition, then do the multiplication by 1/4. But we can distribute that multiplication by 1/4 across the addition. So first multiply by 1/4 and then add. It comes out to be the same value. So 2 times 1/4 plus 3 times 2/4, because there are 2 3s, plus 9 times 1/4 will give you the same answer. And here you are noticing that the average has to do, well, actually, let's run that again. 1/4 is 0.25, 2/4 is 0.5. And so the calculation is equivalent to doing 2 times 1/4 plus 3 times 1/2 plus 9 times 1/4. That is an important observation. Is there a difference between np.average and np.mean? No. look at this last calculation, 2 times a quarter plus 3 times a half plus 9 times a quarter. In that calculation, do you see the number of elements in the list? You really don't. You see the proportions of the different kinds in the list, but you don't see that the list had 4 values. And this says that if we build another list, so I'll just, well, actually, let's just look at the histogram of the list, right? What the calculation here says is, for this calculation, I need the fact that I have values at 2, 3, and 9, and I need these weights. I need a quarter, a half, and a quarter, but I don't actually need to know how many numbers there were in the list, as long as the proportions hold. So this says I can mess with it, right? I can create another list with exactly the same proportions, and look, I actually typed in 10 2s, 20 3s, and 10 9s. Those are the same proportions. The equal numbers of 2s and 9s, and double that number of 3s. Now, I know some of you are wondering, why on earth did you type all this out? That is such bad programming you should have written, but you should have written code to do that. Yes, I should. Except we are trying to look at shapes. Look at that cell here. Can't you see the histogram there? It's kind of on its side, but you see it? Yeah, as a categorical distribution, you can't see the gap between the 3 and the 9, but you can see that it's the same distribution, the same proportions. So I will run this array, and I will join we'll draw the histogram of this new column. And it is exactly the same as the histogram of the previous column. Why did we choose 50 as the total amount of values? Because that was the only number for which I had the patience to type them all out. You could have chosen 500, no problem, or any number that you wished, as long as you keep the proportions the same. So what you're noticing here is that the average depends on the histogram, not on the count, not on the individual, not on the count of numbers in the list. And so now there has to be an interpretation of the average as something to do with this histogram. And can anybody hark back? Some of you will have not, some of you might have taken a physics class. Can anybody hark back to a place where you can think of these as sort of weights attached to a wire? So there's a weight of this size at place 2, there's a weight of this huge size at place 3, and there's another weight of this huge size at place 9. And here, the calculation that we did was this. Value times weight plus value times weight plus value times weight. Anybody remember from an old physics class what that comes out to be? So somebody has a suggestion, and you're correct. It's the center of mass, it's the center of gravity of the system. So I've drawn that picture for you. Okay, so what I'd like you to imagine is this histogram is made out of cardboard. It's a physical system attached to a wire, all right? And what we're going to do is I'm going to run my cursor under the wire, trying to balance that system. Now, if I hold my cursor right there, is that system going to balance, or is the wire going to tip? It's going to tip. It's going to tip to the right, right? If I hold my cursor here, do you think the system is going to balance, or is it going to tip? It's going to tip in the other direction, right? So clearly there's some place along here. This is tipping to the right, tipping to the right, tipping to the right, tipping less. This is 4.25, your average. That is the place where the system balances, right? So the average is the center of gravity of your histogram. In that sense, it is the center. And therefore, don't round it, don't change it. It genuinely means the place where the histogram balances. It is never intended to be one of the possible values in the list. And so let's use that idea. Take a look. So the median is the halfway point. And, just to be very clear about what these distributions are, why don't we assume, I'm looking at this histogram, I'm just going to create a list that has the histogram. One value marked 1, 2 marked 2, 3 marked 3, 2 marked 4, and 1 marked 5. Does that make sense for that distribution on the left? 1, 2, 2, 3, 3, 3, 4, 4, and 5. Okay, great. What's the median? 3. There's a clear halfway point. What do you think the average is? Where does that thing balance? At 3. It's exactly the same, right? So that distribution is symmetric about a point. That point is both the median and the mean. And now what we've done on the right-hand side is we've taken the same histogram, and this last bar that was at 5 has gone for a walk. All right, I just took it for a walk and it ended up at 10. What's the median of the new system on your right-hand side? Still 3, right? Because it's still 1, 2, 2, 3, 3, 3. Your median is right here. The median actually doesn't care what's happening out at the edges. Okay, did the average change at all? Sure, the average changed, because here I was adding up numbers 1, 2, 3, 4, 5 with a bunch of, and here now is the same number of 1s, 2s, 3s, and 4s, but now I have a 10 instead of a 5. So the median, the average is going to increase, right? So the average is going to be bigger. Terrific. Okay, so what you have observed is a general fact. The average is the center of gravity. The median is the 50th percentile. If the distribution is symmetric, then the two are the same. But if the histogram is skewed, and by skewed, I mean it has a tail in one direction, that is called the direction of the skew, then the mean gets pulled away from the median, and it gets pulled in the direction of the tail. So if you have a left tail distribution, then which one is bigger, the mean or the median? You have it. The median is bigger because the mean gets pulled away from it in the direction of the tail, which is left-hand side. You're correct that the median of the previous two histograms were the same in spite of the skew. Yes, and that's one of the reasons the median is used as a measure of the center of incomes and so on, where distributions tend to be very, very skewed. Okay, so now I have a question for you. Here is a histogram. I have deliberately not given you any numbers, right? It happens to be a histogram of an array of a bunch of values, and I'm calling the array X. I'm going to give you 3 expressions, all of which are comparisons, and we are going to look at what they evaluate to. Okay, run your eye quickly. On the left-hand side of all 3 expressions, you have the same quantity. Whatever it means, you have the same quantity. So do you agree that only one of those 3 can be true? More than one cannot be true? Okay, so we have to pick which one is true. So for this, what I'd like you to do is, before we get into what is true and false, just look at the expression on the left-hand side. What is it measuring? Can you tell me a word for what it's measuring? Average, median. Let's try, keep trying. What is it? It's a sum divided by a length. It's a proportion. It's a proportion, very good. It's a sum of zeros and ones, right? This is X greater than NP.average X is a Boolean vector. It is true when X is greater than the average and false otherwise. So the numerator is the number of items in the array that are bigger than average, and then you divide by the length of the array. So that is the proportion, as has been said by a number of people. Thank you very much. It is the proportion of elements of the array that are greater than average. All right, so what you're doing is you are looking at the proportion of this list that is greater than average. Somebody tell me, a proportion on a histogram is measured by what? What aspect of the histogram will tell you about proportions? Area, exactly. Areas represent percent. So you are now thinking about whether the proportion to the right of the average is equal to a half, less than a half, or greater than a half. And I haven't told you what the average is. Because you have to think about, what do you know about histograms with this shape? What do you know about the average of a histogram with this shape? Okay, don't tell me which is true. It is skewed, and it is skewed right, and therefore, what do you know about the average? The average is higher than the median. And the median is a very interesting point because you have the 0.5s here, right? So what percent are bigger than the median, do you think? Just if you had to guess, what percent would be bigger than the median? 50, yeah, that's kind of the defining property of a median. 50% are bigger than the median, because the median is maybe somewhere here. Yep, does that look like the average? Nope, so the average is out here, maybe, I don't know, somewhere. Okay, so now if you look at the proportion greater than average, what are you going to get? Equal to 50, bigger than 50, or less than 50? Less than 50. If 50% are bigger than here, are 50% are to the right of here, then less than 50 are going to be to the right of here. So when you look at a distribution with a tail, you know that the average is not the 50% point. And moreover, you know whether the percent on either side of the average is bigger than a half or less than a half. Okay, let me pause and take questions. No difference between np.mean and np.average. The tail, this thing is the thing that looks like a tail. It's on the right-hand side. Okay, so some people want an explanation. Okay, the median is somewhere here, right? These are very tall bars. The median is somewhere here. What percent is to the right of the median? What percent are bigger than the median? 50. So if 50% are bigger than, say, this point here, right? My average is, say, this point here. Compare the percent that is to the right of the average. What do you think? Bigger than 50, less than 50, what? The people who asked the question. Less than 50. Done. Because the percent that is to the right of this point here, that is included in the percent that is to the right of this point here. So it's got to be smaller. Okay. So what we'd like to do now is measure spread. If the collection of all values is an integer, the median, as we have defined percentiles, will be a value in the list and hence an integer. Okay, so we need to define variability, how far off the numbers are. And so one natural thing to do is to take the biggest value and the smallest value, but you'll have quickly the sense from that that doesn't tell you about the shape, right? You can have, if you take a smallest value in one place and the biggest value to the right of that, you can draw any shape of histogram in between, and you won't learn much from this value, from this measure. So the idea is to measure the variability around the mean, right? We have a precise definition of the mean, and we're going to measure the variability around it. So we're going to figure out a way to quantify this, and we'll just do it by a calculation. Okay, so here is my table. These are the values 2, 3, 3, 9. If I want to find how far off the numbers are from their mean, I better have their mean. So I'm going to call that average value. Okay, now the natural thing to do is to take each value and subtract off the average. We will do that natural thing. These are called deviations from average. And so this is the values array minus what we're calling the average value. And then we will add it on to our table. And you can see that some of the deviations are negative and some of the deviations are positive. Negative deviations correspond to values that are below average, and the positive deviation corresponds to the value that is above average. Something very interesting happens when you add up all of these pluses and minuses. You get 0. This is a fact about deviations from average, any list at all. You do your worst, you create the most bizarre list that you can think of, a list of numbers, calculate its average, subtract off the average from all of the numbers. If you add up, you will get 0. So the average is because it's the balance point, it is a number such that the plus deviations exactly cancel out the minus deviations. But I'm trying to get a sense of how big the deviations are. And so what I'm realizing now is that the cancellation is getting in my way. I can't just take the average of the deviations because I'm just going to get 0 every time. So I want to get rid of the sign. What are 2 time-honored ways in maths of getting rid of the sign? Take an absolute value. What's the other way? Square. Those are the 2 classic ways. Okay, so the absolute value is fine, but it doesn't have nice math properties. For example, there is no nice math formula for what is absolute A plus B, right? You can bound it, but you can't say exactly what it is in terms of absolute A and absolute B. Some of you will know that the absolute value function, all of you will know that if you graph it, it has a corner. Corners are difficult to deal with mathematically, more difficult than if you had a smooth function. So what we are going to do instead is we're going to square. And the measure that we're going to get is going to have very nice properties, and that is why it keeps being used. So to get rid of the sign, we are going to square the deviations. So we're going to look at deviations, square them, and add them onto our table. Okay, so these are such just some bunch dumb numbers. They are the squares of all of these deviations. The variance is defined as the average of the squared deviations. Okay, so it's an average of these squared deviations. And it has the good news and the bad news. The good news is that it's some positive number. We are squaring the deviations to get rid of the sign. The minus signs were causing trouble for us. The minus signs were all canceling out with the plus signs. We were getting 0. We don't want that. We want to get rid of them, the signs. So now we've squared the deviations and we've got this number 7.68. And now we want to understand what it's doing. Okay, so remember the image where these were, the list was amounts in dollars, $2, $3, $3, and $9. Okay, the average is 4.25. What are the units of those? The average is in what units? Dollars, $4.25. So look at this deviation, this $2 minus $2.25. What's the unit? No, the deviation. The deviation is in dollars, right? Minus $2.25 means you owe the world $2.25. This deviation is $4.25, still dollars, all right? Now, we are doing a calculation. Things have to have physical meaning. So thus far, we understand the physical meaning. Everything is in dollars. And now we went ahead and squared the deviations, right? What is the units of a squared deviation? No. You've taken a deviation in dollars and you've squared it, dollars squared. That's the unit of the squared deviation. So when you take the average of the squared deviations and you get this quantity called the variance, what is its unit? These are all dollars squared. If I average them, what's the average, the units of the average? Still dollars squared, because we said right in the beginning, the average has the same units as whatever list you're averaging. Okay, so the variance is $7.6875 squares. I will tell you right now that there is no human being on earth that understands what a squared dollar is. This is really bad news. We have fixed the problem of cancellation, but we have messed up the variance. How can we fix it now? Square root it back now. Take the square root. Exactly. The standard deviation, which is the quantity that is your measure of spread, is going to be the square root of the variance. And that's a number, 2.77 something, and that is in dollars. All right, average $4.25, standard deviation $2.77. That's what we're getting. Now I need to interpret that number, which I'm going to spend the entire rest of the lecture doing in various contexts. But I would like you to go through the calculation that is on this screen and ask your questions. Every step should have a motivation. You don't have to memorize any of this, right? You need to know how far the numbers are from the average, therefore you need the deviations. The deviations all cancel each other out, so you need to get rid of the sign. We're going to get rid of the sign by squaring. If we average those, why don't we just take the absolute? You would not get the same thing if you took the absolute value. You would get something different. Why don't we just take the absolute value? Because the measure that you get there does not have the nice properties of the measure that of this one that I'm just about to spend the rest of the lecture on. Is there no function that calculates the SD? Okay, that's a long calculation. You bet there is. How about np.standard deviation of my array? Okay, and so now we need to understand why this measure and not any other. Okay, so what does the standard deviation measure? It measures roughly how far the data are from their average. It's not measuring how far the data are from each other. It's measuring roughly how far the data are from their average. The standard deviation, we don't give you, that thing that you see there, the SD equals something, that is a formula. Okay, the root mean square of deviations from average. This is a formula, is a recipe for a calculation. This says, step 1, calculate the average. Step 2, calculate the deviations from average. Step 3, square the deviations. Step 4, take the mean. And then step 5, take the square root. And the reasons for all of these moves, you told me why they should be. Okay, so the standard deviation is the root mean square of the deviations from average. It's also known as the RMS of the deviations, this kind of thing. You have a bunch of errors, you square them, you take the mean, and then you take the square root. This process will be repeated in other places with different kinds of errors. And so it's shortened to RMS. And it is applied to errors that are both positive and negative and end up canceling each other out. And this SD by calculation, by definition, has the same units as the data. Okay, why use the SD? Because a lot of people have said, why didn't we just do the absolute value? All right, and you can think of, if you can square, you can take fourth powers. Why this particular one? There are two reasons. And the reason that we're going to focus on today is no matter what the shape of the distribution, if you look at the range average plus or minus a few SDs, you'll pick up the bulk of the data. And don't please start typing in, what do I mean by a few? What do I mean by a bulk? We'll be talking about that. But if you know the average and the SD of a list, you will have a very sharp sense of where the vast majority of the data points lie just from those two numbers. And that is a very important result because it starts with no matter what the shape of the distribution. You can apply to anything, which means you can apply to unknown populations. Any result that starts with no matter what the shape of the distribution is a powerful result. There is also a second reason, which we'll deal with next week, and we will maybe signal today. Okay, so this statement, no matter what the shape of the distribution, the bulk of the data are in the range average plus or minus SD. that comes from an inequality or a bound created by a Russian mathematician called Chebyshev. And so here is a loose statement, right? No matter what the shape of the distribution, the bulk of the data are in the range average plus or minus few SDs. And the two words that are loose are bulk and a few. And what Chebyshev did is he quantified those. So I'm going to give you his result. It's a very, very simple result. You start with any distribution you want, and you look at the proportion of values in the range mean plus or minus any number of SDs. You get to choose Z, but just choose it to be a positive number, just to make sense. You'll get the same interval either way, but we will be thinking of Z as a positive number. Okay, so you look at the range, say mean plus or minus 3 standard deviations. Okay, Chebyshev says that proportion in that range is going to be at least 1 minus 1 over Z squared. So if I look at mean plus or minus 3 SDs, that is an interval in the middle of the distribution. By Chebyshev's inequality, that region contains at least 1 minus 1 divided by 3 squared. That is 1 minus 1/9. That is 8/9 of the data. That's a big proportion. And so that 8/9 is a quantification of your bulk in case by a few you meant 3 SDs. And now you can put in any other number and you will get other bounds. And the bounds look like this. So average plus or minus 2 SDs, no matter what the shape, you're going to have at least 75% of the data, right? Average plus or minus 5 SDs, no matter what the shape, you're going to have at least 96% of the data. And this is important because it says that the average and the SD together give us a really sharp sense of where the values lie. As to why this result is true, you can take CS70 or STAT88 or any of the upper division probability classes, and they will be discussed. We will check in an example that it holds. But I would like you to look at this screen, please, and ask your questions. If you don't ask any questions, I'll ask you questions. Okay, so Z cannot be 0. This is, okay, so you're raising a good question. So Z cannot be 0 because then I wouldn't have an interval, right? I would just have the mean. Okay, so now there's a question, what happens if Z is 1? What does Chebyshev tell you? If you look at the range mean plus or minus 1 SD, right, then what is the bound here? Yes, but he doesn't say 0. The bound, it is at least 0. So for Z equals 1, the result is saying the proportion of values in the range mean plus or minus 1 SD is at least 0. Is that a true statement or a false statement? That is a true statement. It's a proportion. It's going to be at least 0. You don't need Chebyshev or anybody to tell you that. True and not useful. Very good. That is exactly right. And while we are being a little persnickety, what happens if you take Z equals a half? If I look at the range average plus or minus half an SD, careful, minus 3, exactly. Minus 3. So if you take Z equals a half, then Z squared is 1/4. 1 over Z squared is 4. You get 1 minus 4, and that's minus 3. It's an integer. You get minus 3. So what this bound is telling you that if you look at the 0.5 doesn't have to, the Z doesn't have to be an integer. It's just a number. So if you look at the interval mean plus or minus half an SD, this bound is telling you that the proportion is at least minus 3. Is that a wrong statement? It's completely unhelpful. It is a true statement. The proportion is in fact at least 0. So it's definitely at least -3 or -17, but it doesn't help us. So what you're seeing is that this bound is actually useful when you're actually walking away from the mean for a little bit, right? And then saying what is contained in your regions. Okay, so what we're going to do is we're going to look at a table that by now you know very well. And we are going to look at a bunch of distributions. So these are all numerical variables, and you can see the distributions all have different shapes. Okay. And but Chebyshev's inequality works for all of these shapes. How does this relate to the empirical rule of 68, 95, 99.7? That empirical rule works for only one kind of distribution, and that is the bell-shaped distribution. If somebody gave you that rule without the conditions, they shouldn't have. We'll talk about 68, 95, 99.7 later. How did I create so many histograms with one line? Okay, I put overlay. I said births.hist. I did not specify the columns, so it will draw the histogram of every column. And I said, don't overlay them because it doesn't make sense. They're all in different units. All right. And then you get the whole lot at once. Okay. Okay. So what we're going to do is we are going to look at where are the. Okay. We're going to look at this distribution of the pregnancy weights. And this is clearly a right skewed distribution. And we are going to compute the mean and the standard deviation of these. And call them mean and SD. So here you have a distribution. And now we are going to look at the, we're going to restrict the table only to where the pregnancy weights are in the range mean plus or minus 3 SDs. So in that, they are between mean minus 3 SD and mean plus 3 SD. We'll create that table. It's called within 3 SDs. So now what do I do to this table to get the proportion that are within 3 SDs? What do I do? From my big table, I have extracted the mothers that whose pregnancy weights were in the range mean plus or minus 3 SDs. Great. I do num rows. Now, is that a proportion? It's a count. So I have to divide. And I guess, how about relative to the rows in the original table? Does this look good? Great. Okay. So we get 98.6%. Okay. Now, what does Chebyshev say? Chebyshev says that this is mean plus or minus 3 SDs. So the bound is at least 1 minus 1 over 3 squared, which is 88 point whatever percent. Okay. So is our observation consistent with the bound or not consistent with the bound? It's consistent. Okay, great. So I actually have something in this notebook that is a way to check for all of the variables for a whole bunch of z's, whether the bounds are consistent. It is consistent because Chebyshev says the proportion should be at least 88.888%. The proportion is 98.6%, which is at least 88.88%. Remember that Chebyshev is only giving you a bound. It is not going to give you an exact value or an approximation. It just says at least something. Okay, terrific. I'm actually going to skip a computation of checking that the bound works for various z's for all of these, because I'd like to go to interpretation. Otherwise, you will be left over the weekend with a very strange sense of what this measure does. So what I'm going to do is talk about standard units. Now, you saw all those histograms. They were all on different scales. Some were heights, some were weights, some were ages, and so on, all on different scales. But when we want to talk about the shape, it sort of doesn't matter what the units of measurement are. We have to have some way of talking about histograms without being caught up in whether it's kilometers per second squares or not. And so here now data scientists, statisticians have a great way of thinking about data. which is they set the origin of the data to be the mean, and they measure in units of SDs. They measure in units of standard deviations. So what they do is they define a new scale called standard units. So here's your original scale, right? If it was ages, then these are all in years. And there's some mean. What they do is, okay, this number, this mean, I'm going to call 0 on my new scale. Okay, and then I'm going to set the scale by walking 1 SD to the right. This is mean plus 1 SD. I'm going to call that 1. This number here is mean plus 2 SDs. I'm going to call that 2. Similarly, mean minus 1 SD, I'm going to call it minus 1. And mean minus 2 SDs, I'm going to call it minus 2. And in between, all the numbers can be filled in like that. Okay, so what I'm measuring is how many SDs above average is my number. Now, we can clearly see what the corresponding values should be if you go even, integer numbers of SDs on either side. But what is the calculation? We are taking a value, we are subtracting off the mean. That gives me a distance in years. And we are trying to see how many SDs in that is that. So we look at it relative to an SD. This number is called standard units, also colloquially known as the Z-score. And so what does it measure? Actually, let me ask you, let me take questions on the scale there. Okay. So what it measures is how many SDs above average, not away from average, but above average. So when it's minus, then the value is below average, right? And what you've done is you relabel the mean and the SD. When you convert a list to standard units, the average becomes 0 and the standard deviation becomes 1. And there are no units of measurement whatsoever. It's just how many SDs above average is what you're counting. And so to convert a list to standard units, I will take an array. I will take my array X. I will subtract off the mean from each value. This is an array operation, not a numerical operation. And then I will divide by the standard deviation of my list. Okay, so here is the column of births, and here is the column of here's the column of ages. Here is the column of ages in standard units. If I run this next cell, mean of the ages in standard units and standard deviation of the ages in standard units, what will I get? If I convert to standard units and then take the mean and the SD, what are the two numbers that I'm going to get? 0 for the mean and 1 for the SD. And let's see if we get that. That is exactly what we get. This is Python for 0, right? It's a tiny, 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 tiny number. And the SD is a clean 1. Okay, great. Okay, take a look at that. These are actually the ages and the corresponding standard units. Just take a look. I've given you the first 10 tables. Tell me, what was the average age? What are you looking for? Based on those 10, you're looking for standard units of 0. And what do you see? 27, that's the closest you can get to the average. This is the smallest, the closest to 0, 27. Okay, for SD of the ages, what standard units are you going to look for? 1, okay, so if I look for 1, I'm getting to 33. Is 33 the SD? No, because that's the distance from the mean is the SD. And so 33 minus 27, 6 should be the SD. And we should go and check that. So here's the table. And the mean age is 27 and the SD of age is about 6, which is what you told me by eyeballing that table. Okay, what I've done here is I've drawn the histogram for you. This is a histogram you've seen many, many, many times. And here is the redrawn histogram where the ages are measured in standard units, right? Really no difference between the two histograms other than what numbers are being written down here. It's just a change in units of measurement. Okay. But if you look at this histogram, right, the 27, yeah, you kind of see, okay, maybe it's going to balance somewhere here. Is it easy to spot why the standard deviation should be 6? I don't think so. I really don't think it is easy to spot why the standard deviation should be 6, right? In fact, the standard deviation is not easy to see by eye. So when we come back on Monday, we will talk about the second reason why the SD is so important, which is that it has a very deep connection with the bell-shaped curves. And bell-shaped curves arise a lot for reasons of probability theory. Okay, I will stop now.